which is not interacting with the photon baryon gas. So let me just show you that. So what I'm going to show you is what is predicted. So the red curve here is the prediction of the standard model, which has dark matter and a cosmological constant, all the things you either like or hate. So that's the prediction of the standard model. Let me show you how this prediction changes if I keep everything fixed except the amount of dark matter. So what happens, because I keep the geometry fixed, as the dark matter goes down, it's compensated by the cosmological constant in this case, but everything else is kept fixed. So that means that here, this is the overall amplitude, that stays fixed. But look at the difference in the heights of the peaks, and in particular the relative heights of the peaks. This is not a small effect. This is going by 10% jumps from the full amount of dark matter in the first one, which is the model, standard model, to no dark matter, which is the last one. So this is not a subtle effect. It's huge. So if we look at then what they say, this is the parameters measured by fitting this to the standard model. This is the fraction of the energy density in the universe in the dark matter. 23% plus or minus 1.5%. This is a 30 sigma measurement. Actually, more than 30 sigma. Okay. Notice also, this is the measurement of the baryon density, 4.5%, also a 30 sigma measurement. So what you learn from this is the sound waves that we see, the material which is actually interacting with the photons is the baryons, it's this amount. But these waves are being driven by something else, which has to be clumped, it's driving the oscillations, and which is much larger. Interestingly now, the data have got so good, they can put additional limits on other things. So this is a particularly interesting one for a second table in the same paper. This is the total upper limit on the total mass in neutrinos. Now, it's 0.6 eV squared. Actually, if you turn this into an upper limit on the density neutrinos, it turns out they have to be substantially less than the density of baryons. So at least within the standard gravity model, now the data require the total mass in neutrinos to be not more than about a quarter or a half of the mass in baryons. So conclusion from this, at an age of 400,000 years, the mass energy content of the universe was dominated by a non-relativistic, non-uniform component, which had only very weak or gravitational interactions with the baryon photon fluid. And this component could not consist of neutrinos or any other known elementary particle. So then, according to the standard picture, most of our universe today is the dark energy, which we're not talking about here. Roughly 22% is the dark matter, 4% are the atoms, the stuff we actually know about. So this gives us, in the standard model, very well specified initial conditions. So you then ask, how do they grow? This video shows that you start, this is now a calculation of the nonlinear evolution from these initial conditions, assuming Einsteinian gravity. And so what you see is the contrast, this is the expansion of the universe is taken out, gradually grows, the material streams out of low-density regions into high-density regions, streams along these filamentary structures, and makes objects. So this is the nonlinear prediction of evolution from these linear initial conditions, assuming Einstein gravity. So this, you can see, then makes very detailed predictions for what the universe should look like today. And that was the video I showed at the beginning. This is just a fly-through of a virtual universe showing you the range of dark matter structures that are predicted in the present universe by the standard theory. You can see it's no longer smooth at all. There is an enormous range of structures from relatively small lumps like this, which might host the Milky Way, to big lumps like this one we're homing into, which would host a galaxy cluster like the one that Zwicky looked at, according to the standard picture. Okay, so this then is the prediction. So we not only have a very detailed fit to the initial conditions, which requires the dark matter, but in the standard model we can predict in considerable detail what the dark matter distribution should look like today. So the question then is this supported? So the first thing you saw there is that as objects grow, the material has to stream out of the low-density regions into the high-density regions. So these motions can be detected. So this is another quite precise measurement of this. Now at a redshifts between 2 and 4. So this is when the universe is between about 1.5 billion years old and 3 billion years old. And what's shown here is structure in the gas, the diffuse gas between galaxies, which is observed through the absorption it causes in the light of background quasars. And so then this is a characteristic, this is a wave number, so this is a characteristic size, small wavelengths, long wavelengths. The data here are the data points at different redshifts from about 3,000 quasars. The curves are not joining the data points. These are actually a model based on the standard lambda CDM for what is expected. And the reason the bumps are here is because this actually depends on the actual redshifts of the quasars that we used. And so you can see there's a very detailed agreement. So this means that at redshifts between 4 and 2, the density and velocity perturbations in the diffuse pre-galactic gas are very close match to those predicted for dark matter-driven quasi-linear growth from the structure we see directly at a redshift of 1,000. So this is a consistency check. We can do this at redshift 0. This is the distribution of galaxies in the nearby universe on the whole sky from this survey. Now, in linear theory, the velocity, our velocity relative to the overall expanding universe, is given by the gravitational force we feel times the time available, with a constant coefficient here that's very close to 1. So you can actually measure this peculiar velocity, because we see this as our motion relative to the microwave background. And this is measured very accurately. It's about 600 kilometers a second. We can estimate the gravitational force by looking at the distribution of galaxies. So we can see the gravitational force only comes from the inhomogeneity. If the universe was smooth, there would be no net gravitational force. Because it's not smooth, there's a gravitational force, and we can observe the lack of smoothness in the galaxy distribution. But then we have to relate the galaxy distribution to the amount of mass. So the assumption, the parameter you actually measure, if you compare the galaxy distribution to this number, is this one, which involves the mass density of the universe, which is dominated by the dark matter, and the amplitude of the fluctuations in the dark matter to the fluctuations in the galaxies. It's what's called the bias parameter. So this is the parameter that's actually measured from this comparison, and this is the value you get from these data and this number. Now, each of these parameters, both omega and this bias for these kinds of galaxies, are measured directly in the standard model. So you can ask, what should you have got? This is the answer, within 1 sigma. So the conclusion then is in the present day motion of the Milky Way is linked to the large-scale distribution nearby galaxies, just as expected for linear growth according to standard gravity from a universe which started with the properties you see in the microwave background. And you can do the same test for the detailed velocity field on large scales in the local universe, and you get essentially the same result. This is a picture of the predicted dark matter distribution from the simulation I just showed you. According to the standard picture, the galaxies we see formed as gas condensed at the center of each of the dark matter lumps. So you can model that in a physically reasonable but approximate way and predict what the distribution of light should be. So inside the computer, you now have a prediction of where the brightnesses of all the galaxies in your computer universe would be. So you can send in a virtual telescope, observe the virtual universe, and make a survey of the virtual universe you compare with surveys of the real universe. And this is what you get. This is a survey of the galaxy distribution in the real universe. We are here. This is distance away from us, and this is one angle on the sky. And this is a redshift survey. This is a survey of the virtual universe made in exactly the same way. These are surveys of the real universe at a different scale. That's why the structures look bigger here than here. These are surveys of a virtual universe made in the same way. So what the question then is there a good statistical match? And the answer is, by most statistics, the match is actually quite close. So what you learn then is the statistics of the large-scale distribution of galaxies agree in detail with those predicted for growth according to standard gravity from the initial conditions seen in the microwave background, assuming that galaxies form when gas condenses at the center of all these dark matter halos. Right? So if you make these assumptions and work it through, you can get a close fit. Let's come to individual objects. I won't show you the update of Zwicky's test, although with better data, his result still holds. This is a different observational test of rich galaxy clusters. If you look at rich galaxy clusters, they contain a static atmosphere, or nearly static atmosphere of hot gas which emits in the X-rays. And so you can measure its density and its temperature directly with X-ray telescopes. If it's sitting there in equilibrium, then if you know the density and the temperature is a function of position, you can use the hydrostatic equilibrium equation to figure out the potential well, and that gives you a mass measurement. So this is masses measured in this way. This is a mass. This is radius, both logarithmic. So there are, I think, 10 clusters here. And then this is a prediction for the standard model. And there's effectively no real free parameter here, because the temperature is adjusted, is measured for the global temperature. That's what you adjust to the model, and then you just put the mass on. Okay, so that's the level of fit that you get. However, you can look in other ways. You can use gravitational lensing. You see these strongly distorted objects, the background galaxies being gravitationally lensed by this rich cluster. You can use the gravitational lensing also to measure the masses of clusters. So now this is very complicated, but all you need to know is there are 6 panels here, which are clusters of different inferred masses from 10 to the 13 to 10 to the 15. The data points are the distribution of mass inferred from gravitational lensing, and then the curves are what is inferred by the standard model. And here, the way these are fit, there are essentially no free parameters in this fitting, because we've used the number count of the galaxies to decide which cluster should fit. And you can see, in all cases, it fits quite well. There are small offsets, which maybe we have the wrong parameters for the standard model. So the conclusion then is that mass structure of galaxy clusters inferred by standard gravity agrees in detail with that predicted in a cosmology which fits the microwave background and includes dark matter. And this is true whether you use galaxy motions, hydrostatic equilibrium, or gravitational lensing. And the latter is important because it means that both the photons and non-relativistic particles, like the galaxies or the gas atoms, are affected by the unseen mass, or whatever it is, in the same way as predicted by by general relativity. Here's a famous case. This is a cluster where you can see it has 2 pieces, one of many galaxies here and many galaxies over here. If you infer the mass distribution from gravitational lensing, you find most of the mass appears to be in these 2 places behind the galaxies. When you look with an X-ray telescope, you find most of the observed material is actually here and here in the middle. So it seems that the mass detected by lensing agrees in its distribution with the positions of the galaxy clumps, which in terms of the baryon mass are actually subdominant, and does not agree with the position of the X-ray gas, which is the baryonically dominant component. So that suggests that there must be another more massive component, or something which is sourcing the gravitational lensing, which coincides with the galaxy positions. This is satellite galaxies. Let me skip to this. So we see many galaxies orbiting individual halos. So we can ask, what is the relation? Can we make a measurement of the relationship between the mass of a galaxy? This is in solar masses. Our Milky Way would be here somewhere. This is the mass of the galaxy and the mass of its dark halo. And this is what you get from 3 different arguments. The circles here inferred by gravitational lensing, just as we saw for the dark matter clusters. This is the relation. This is obtained by stacking lensing results for many galaxies. The triangles are inferred by using the dynamics of the small galaxies orbiting around the big ones, again averaged over samples of large numbers. And the curve here is what you get just from a counting argument when you count how many lumps there are as a function of mass in my random CDM universe, how many galaxies there are as a function in the real universe, and if you assume there's a one-to-one relation between the mass of the dark matter and the mass of the thing you see at the center, then you can predict how these should be related. That's this curve. You can see all 3 of these ways of inferring the mass of the dark matter around a given halo agree with each other. So the conclusion is the mass structure predicted by the standard cosmology for the dark halos of isolated galaxies agrees as a function of their stellar mass with that inferred directly both from lensing and dynamical data. And this way of looking at the comparison had no free parameters. I'm going to skip this to get to dwarf galaxies since I'm running out of time here. So I think Pavel will probably talk about dwarf galaxies, so let me introduce this. So these are the smallest galaxies around the Milky Way. Their luminosities, the Milky Way in these units has a luminosity of about several times 10 to the 10. So this one is already less than 1,000th the luminosity of the Milky Way. You see we have about 5 orders of magnitude in the brightness, the number of stars in the objects. And this is the mass inferred from their motions within a standard radius. You see the rather surprising result, the mass inside this standard radius appears not to depend on the luminosity. So it looks as though the apparent mass of dwarf galaxies is independent of their baryonic content. So it seems as though whatever's causing the motions is dominated by a different component.